Hello, I'm Duncan from Cambridge Quantum Computing. I'm quite sad that we can't all get together in California to have our conference where we can discuss things in person, but I'm happy to have the chance to send you this transmission from sunny Cambridge in England to tell you a bit about the work that CQC have been doing in collaboration with Honeywell. We've been working with Honeywell since the time that their first ion trap devices came online. And we've done many experiments to try and discover how to get the best of these devices. For example, we recently did a Bell experiment on one of the Honeywell ion trap systems. So it's a Bell experiment, it's not loophole free, but because of the extremely low crosstalk between the qubits in this system, we were able to observe a Bell violation which is a lot bigger than any previously reported Bell experiment. And of course, we're using a general purpose quantum computer to achieve this, not a specially designed experiment. I should emphasize, we're not interested in proving that quantum theory is correct again. I think we all believe in quantum theory now. What we're using this for is a source of randomness which is verifiable, perfectly random and private for use in cryptographic applications and also in Monte Carlo simulations. In another piece of recent work, we've studied optimization problems in Honeywell systems. The plot that you can see on screen now is showing a knapsack problem. So this is an abstract problem, but it's very interesting if you care about packing boxes into lorries or assigning jobs to workers. So this was solved using the variational quantum eigensolver. And you can see in the plot that the lowest energy state corresponding to the optimal solution of the knapsack problem is selected with very high probability. The variational quantum eigensolver is best known as a chemistry algorithm. A lot of other techniques from quantum computational chemistry can also be adapted for business problems. Now, this algorithm relies on having high fidelity gates and as few of them as possible. In the Honeywell systems, they have all-to-all connectivity, and this saves us from spending our fidelity budget on gates which only serve to move the qubits around the system. Both of those problems illustrate some of the kind of generic features that you would expect to find in a good quantum computer. But I want to focus today on a distinctive feature of Honeywell systems, which is the ability to do mid-circuit measurements. So in a quantum computation, I have to do a measurement at the end of my computation to get the data out. It wouldn't be very interesting to do the quantum computation if the data could never be extracted.
Precious data.
The first essential difference between a classical computer and a quantum computer is that when you measure the state, when you try to read the state out at the end, you've actually changed it. So if you ask a yes-no question to a quantum state that was 50-50, then afterwards the state is irrevocably yes. Make your own Brexit joke here. This might seem like a minor point, but it's quite important that it's not actually necessary to measure all of the qubits. There are some algorithms that work this way. You measure a single qubit at the end, and all the others can just be discarded. So that may seem kind of trivial, but once you put partial measurements together with the collapse of the state caused by measurement plus quantum entanglement, then interesting things start to become possible. So as the name suggests, a mid-circuit measurement is when you perform the measurement in the middle of the computation, and importantly, the computation carries on afterwards, right? And this wouldn't really be all that exciting if you couldn't use the result of that measurement in the later part of the computation. The most important use of mid-circuit measurements of this kind is not on today's agenda, but that would be for quantum error correction codes. If I want to detect an error, first of all I have to measure the error syndrome, however that's achieved, and then if I want to correct the error afterwards, I have to intervene in my circuit based on what error I detected. For today I want to focus on two other uses of mid-circuit measurement, the first of which is assertions, and the second of which is measurement-based quantum computing. So assertions are a very common idiom found in programming, and it basically allows the programmer to state the assumptions that this piece of code relies on. And so the assertion says, please check that my assumptions hold, and if not, abort. So if you look at my silly example C program on the slide now, it's going to check that the array indexes are actually valid, and if they're not, then the program will fail. The intention of assertions is that they're supposed to catch bugs, like programming errors. So if we want to have assertions for quantum programs, then we need to be able to state our assumptions about the quantum state, and we have to have some way to check those assumptions. So way back in 1936, Birkhoff and von Neumann basically foresaw the need for quantum programmers to debug their software 100 years later, came up with the idea of quantum logic. To long story short, what quantum logic says is that the only valid statements you can make about a quantum state are saying which subspace of the Hilbert space it lives in. And since subspaces correspond to projection operators, when the quantum programmer wants to make an assertion, they're basically naming a projection operator that they claim will leave the state unchanged. This idea that assertions are projections is not our idea. You can read a very nice approach in this recent preprint from Gushu Li and his co-authors. So they describe exactly this kind of assertion facility, and if you want to learn more about that, I can recommend Gushu's talk at the recent Quantum Compilers workshop. So to see how this might work in practice, we'll take an example from their paper and show how it would work in PyTicket. We're going to make an assertion right in the middle of this circuit, and the assertion we're going to make corresponds to the operator A2, which you can see on the screen. And on the other side you can see the code, and I've put a comment to indicate where the assertion will go. So the assertion says that the first 2 qubits are both in the plus state, and the final 3 qubits are in the GZ state. Here is some code for how this might look. We're defining the projections in terms of Pauli operators. I should emphasize that this feature is not yet available in PyTicket, and it is likely to change before it ships, so don't pay too much attention to this code. The compiler will insert an appropriate subcircuit to measure the projector corresponding to the assertion, and combine all the individual measurements into one bit, which tells you whether your assertion passed or not. This is a pretty extreme example of an assertion because we've asserted exactly what the state has to be. In general, you'd want to only pin it down into a subspace, in which case you'd be measuring probably only 1 or maybe 2 qubits to do this. At the current state of technology, device errors are more of a problem than programmer errors. Fortunately, we can use assertions to help with device errors as well. To illustrate this, I'm going to describe a computational chemistry experiment we did recently. So we're going to try to find the ground state energy of this chain of hydrogen atoms. So this is H3+, so 3 atoms but only 2 electrons, that's why it's plus. That can be encoded into a quantum simulation using 6 qubits. So we want to write down a circuit which prepares the ground state, and then we want to measure the energy. Naively, you would probably come up with a very large circuit, more than 300 2-qubit gates, but using the human chemistry package and the ticket compiler, we can reduce this to just 15 C0 gates. But we can do more. If you look at this molecule in the pictures, there's a mirror symmetry here. And any quantum state which doesn't have this symmetry is something unphysical, and it can only happen if something's gone wrong during our calculation. The symmetric states live in a subspace of the Hilbert space, which is defined by the projector which I've written on the screen here. So we can check this at runtime using an assertion. We first find a place to cut the circuit. We insert the assertion of the projector, and the compiler will insert the runtime check. And should the assertion ever fail, then we know that that run should be discarded because a device error has taken us into an unphysical state and the rest of the execution is nonsense. So does this work? We did a single point energy calculation in 2 variations. The first variation is just the plain ansatz, no symmetry verification, no assertions. In the second one, we actually verified the mirror symmetry I mentioned earlier and 2 others. So these assertions don't come for free. In total, we had to add an additional 10 2-qubit gates to the circuit and also 3 measurements. However, despite almost doubling the size of the circuit, the additive error in the energy calculation is almost halved in the version with symmetry verification. So we can see that this technique of symmetry verification has some merit. Let's move on to our second topic, measurement-based quantum computation. We're going to focus on the one-way model, which was introduced by Robert Rossendorf and Hans Briegel back in 2001. It's amazingly beautiful. It gives a completely different perspective on how quantum computation works. The idea is very simple. You start with a large generic entangled state called the cluster state, and then you perform single qubit measurements on that state. And that's a universal model of quantum computation. We're relying on the fact that doing a measurement will collapse the state and thus advance the computation. And we're relying on the fact that we can decide what measurements to do later after we've seen some earlier measurements. I'll try to explain this with an example. So we're going to need a quantum circuit. It doesn't really matter what it does, anything we do. And it's going to be a lot easier to see what's going on if we use the ZX calculus. So let's translate this circuit notation into ZX. All I've done is change notation. This is exactly the same circuit, exactly the same vector as in circuit notation. The ZX rules say that I can merge dots if they're the same color. So let's do that too. Simplify the picture again. Mathematically speaking, this is still exactly the same thing. In the circuit picture, we were looking at the description of a vector in terms of applying some unitary gates to an earlier vector. In this picture, it's more of a tensor network description of the state, but it's still the same state. However, in this picture, the connection to measurement-based quantum computing can be more obvious. So roughly speaking, the dots correspond to qubits, and the lines show the structure of the cluster state. Now the colors and the labels on the dots tell you what measurement I'm going to do to that qubit. To run the circuit in this model, we just have to measure all the qubits. For simplicity, I'm just going to assume that we're going to go from left to right. So let's look at measuring one qubit. So we shine our laser on it, or whatever it is that we do, and after a while we get the answer +1. Okay, great, everything worked as we expected. We can just go on to the next qubit we want to measure. However, approximately half the time we'll see the other answer, -1. And this means that we've got an unwanted Pauli term introduced into our computation. So we can use a bit of algebra to push this Pauli term forwards into the computation. And in this example, we're going to push it all the way to the end. I'm not going to explain the rules of how to do this, but if you know what stabilizers are, then you already understand what's happening here. So we can push this particular Pauli term all the way to the outputs, which means that we can classically correct for this after the computation is finished. Now that's not always possible. If we have any non-Clifford elements in our circuit, like this delta here, then we might have to do more. So if I measure this qubit, again in the +1 case everything is great, but in the -1 case I have Pauli error, and it has to go past this delta. And in order to do that, I have to take the Pauli into the measurement. So this delta will either be plus delta or minus delta, depending on that measurement. So we did this using the Honeywell H0 system, using bigger and bigger clusters built from a repeating layer corresponding to this CNOT circuit. We had to stop at 17 layers, which is a cluster state of 105 qubits, which is a pretty big cluster state considering that the H0 system that we used only has 6 qubits. So obviously a trick had to be employed. And the trick is a very simple one, that although in the end we'll use 105 qubits, we don't need to have them all at once. And so we can build up the cluster layer by layer in a just-in-time kind of fashion. Our intention was to keep going until we hit the noise floor. However, once we got to 17 layers, we could still see the correct answer above the noise. Then we had to stop hogging the machine and let someone else use it for a while. So if you're counting, it's 172 C0 equivalent gates and 105 measurements, and we could still see the correct answer at that point. Okay, so that was fun, but why would you care? So there are two reasons why we were interested in it. The first one is because we're interested in what I call mixed model computing, which means that we want to use either a circuit paradigm or an MBQC paradigm in different places in the same program. And by doing this, we can use the resources available to us in the quantum computer in the most efficient way. The second, perhaps more surprising application is for error suppression. So in quantum systems, we usually recognize two kinds of errors, the incoherent kind, which are uncontrolled interactions between the quantum state and its environment, or the coherent errors, which correspond to some kinds of imprecision in the control of the quantum state. Coherent errors are systematic errors, and thus they often have a preferred direction. We model incoherent noise as a depolarizing channel, and we model the coherent noise as random perturbations to the gate parameters in the circuit. So the incoherent noise is relatively well behaved, but the coherent noise basically increases the spikiness of the distribution, and that shows up in an increase in the RMS error in the data with respect to the ideal depolarizing channel. This data is all very preliminary. Take the results with a big dose of salt. We see good agreement between the model in simulation and the actual performance of the device. In an MBQC computation, we always have these Pauli terms coming from the results of the measurements. And these random Pauli terms act to randomize the direction of the coherent errors, which tends to suppress them on average. When we compare the results of the circuit execution with the MBQC version of the same program, two things are apparent. Firstly, the per operation error rate is significantly reduced, and you can see that by the fact that these curves decrease more slowly in the MBQC version. And the second effect is that the RMS error shows a factor of 4 decrease compared to the circuit. And that's good evidence that the coherent error channel is being suppressed in the MBQC implementation. Two final points. First is that in the MBQC implementation, we see a significant contribution to the overall effective error from the readout error in all these measurements that we're doing, which are just not in the circuit version. If the readout error is reduced, then all these numbers are going to get much better. The MBQC version does have significantly more operations in it than the plain circuit version. And because of that increase in the number of operations, we don't see an overall improvement in fidelity. But I'm not greatly discouraged by that, because we've used the most naive translation possible from the circuit to the MBQC implementation. And with a better translation, the advantage in terms of operation numbers that the circuit has would be greatly decreased. Okay, that's all I have to say. I hope you found it interesting, and I look forward to seeing you all this time next year, hopefully not in my back garden. Bye!